Okay. Um, the reason I gave you this as a take-home problem, I wanted you to um, have more information than you can use to do the problem. Like you needed to use seven of those assumptions. So you had to go through those assumptions and figure out which ones were germane and which ones were not. So we're going to need how many gallons of gasoline per tank? Let's see what else. We needed to know that 2011 was not a leap year. We needed to know how many grams of carbon dioxide per mile were emitted. The average gas mileage for the American car used 23.3 miles per gallon, one car per family, and the average family size in the United States is 3.16 people per family. And each car uses one tank per week. And then we need to know the population of the United States in the year 2011. So those are the assumptions and conversions you needed to use this problem. Okay. So a good place to start is with the amount of people. So we're looking at okay, the next thing we need to figure out is how many families are in that amount of people. Okay, so what? Oh, yeah. Right. Okay, so that goes to families. And there's one car per family. That gives us the amount of cars. Oh, and then there's one tank per car. I'm officially running out of room. um, let me just start this over. Okay, so that'll give us gallons. Okay, and then let's see. Now we're going to go to miles driven. And that was 23.3 miles. Okay, and then we're going to use carbon dioxide. Where is it? Okay, and that'll give you a so people canceled, families, car, tanks, gallons, miles canceled, leaves us with grams of carbon dioxide. Did you have okay? Yeah. Oh, that's right. This is per 1 week. Okay. And how many weeks are in a year? 52. Yeah. There. That'll give you for a year. Thank you. Now, when I look at your version of the problem, I haven't graded this particular problem yet for the class. Typically, as I given this problem last spring, and about half the class got 20 out of 20 points, and the other half got anywhere from on the average about 10 points out of 20. And that's the average. Some people got a 2 because you didn't do anything, and other people got like 18 or something, which is varied. For example, if you stopped on week per week instead of multiplying by 52, you'd probably get 18 out of 20. You should have the guts there.
Should have the what?
Hmm?
Say you should have
The guts of the problem there. Yeah, that's why you 18 out of 20. Yeah, I mean the main point of having giving you this problem was for 2 reasons. One is to go through and see which assumptions are valid and which ones you don't need. And number 2, I just wanted to have a long conversion process. And I gave you days to do it, so you had a lot of time to do it. Okay, so any questions about this guy? All right. And the answer, what is 7? Now, as I was flipping through the tests, I know some of you got this answer because I remember 10 to the 14th. So it kind of stood out. All right. Any more questions about this problem? Okay. Now, we're going to start Unit 2 today. Unit 2 and 3 have very little math in them. Very little math. Okay, so let's talk about the periodic table. Now, the periodic table was not really invented. It was more actualized by two people. A geologist was first, and then a physicist was second. And the physicist is usually credited with coming up with the periodic table. The geologists actually came up with the idea first, and they were both from Russia, but the geologists didn't publish. And in science, if you don't publish, you're not given credit for anything. So Mendeleev was the one that actually published this. Now, what he did is he had a whole bunch of elements at the time. Now, right now, there are 118 elements. And at the time, we're probably, at his time, with 20 or so, not very many. And what he did is he put them in order of, in a one-dimensional in increasing mass for a given dimension. And he noticed something. They also started realizing the chemical properties of these elements that they had at the time. And he noticed that every so often, the elements would have similar chemistry. In fact, extremely similar chemistry. And so what he did, instead of having a big long row of elements, he chopped that row up so that every time the element kind of repeated itself in terms of chemical characteristics, he would chop it there. So for example, he would chop it there and then move this over here. So you end up with something like this. And that's how we went from a one-dimensional concept to a two-dimensional, which is how we ended up with this guy here. So a couple things now. There are columns and rows in the periodic table. The columns are called groups. And the groups have similar chemistry. Now we're going to learn in Unit 3 why that is so. But for right now, similar chemistry. So anything vertical, so that means hydrogen, lithium, sodium, potassium, etc., all have similar chemistry. You need to know 4 groups. Now on the test, I'm going to give you a periodic table. You're going to have to identify different parts of the periodic table. Okay, the first group over here in the far left is the alkali metals. Alkali metals. The next one over is the alkali earth metals. And on the far right are the halogens and noble gases. Now, from now to the end of the semester, I'm going to be talking about this trend in the universe. Things go from unstable to stable, not the other way around. And usually energy is given off at the same time. So if you're going to go the other way, we talk a lot about this in organic chemistry. If you go the other way, you have to supply energy to go to a more unstable state. On the periodic table, everything is basically unstable except for the noble gases on the far right. And the reason for that is they're stable the way they are. Everything else is not particularly stable. That's why you always find them bound up with something else, usually the oxide, what they're bound up in. So helium is very stable because it's a noble gas. We're going to also learn why it's stable in Unit 3. So everything else you won't find by itself. You won't find hydrogen by itself. You find hydrogen gas, H2, but not just H. Carbon's always bound up. Iron, usually you find iron is what? Find a chunk of iron out in the field. Is that pure iron? No, it's rust, bound up with oxygen. It's the oxide. So everything then has some combining ratios. And that's one of the weaknesses of students going into 1A and 2A is naming those compounds. So we're going to spend a fair chunk of time learning how to name chemical compounds. Okay, so vertically, chemistry is the same, or very similar anyway. Horizontally, there's not a lot you can say as you go across the row. Now, rows in the periodic table are called shells or periods, and there are 7 of them. We can talk about the first period, the first shell, all the way to the 7th one. Now we know this goes out to 118. This is an older periodic table. We haven't found anything past that. Okay, so there are names for all the groups, but they aren't used very much. The groups I'm going to have you learn for this this unit are very commonly used. Halogens, noble gases, alkali metals, alkali earth metals. Those are used very commonly. The others have kind of a Latin or Greek name to them, and they're just, no one ever talks about the groups. They exist, it's just that no one talks about the name of it. Okay, so let's look now at, on the period. As you go across the period, the mass, it's called a molar mass. We'll learn about that in Unit 4, but the molar mass increases as you go across. And the size gets smaller, those two things. So the mass, molar mass increases, size gets smaller. Now let's look at at a very minimum, each element in the periodic table has this information in it. Okay, at the very top is how many protons are in the nucleus. How many protons are in the nucleus? Also, you have a symbol. And in the periodic for our class, it also gives the name. When you get to 1A and 2A, they're not going to have the name there. It'll just be, it'll look like that. And on the bottom is something called the molar mass. And that's the average of all of the isotopes in the world. I'm going to talk about what an isotope is in a minute. Okay. Now, when you write an element, except for the periodic table, these numbers are flipped. So the 6 would be on the bottom. We were going to write it for carbon like this. Except on the periodic table, it's flipped.
Periodic table 12.
The protons are on top, yeah, but the smaller number on the periodic table, smaller numbers on top. Okay, so when you write it outside the periodic table, the smaller numbers on the bottom. And that's the number of protons. It's also called the atomic number. Atomic number. So number of protons, atomic number, same thing. Yep. And then the molar mass on the bottom is the decimal number. And the reason why it's a decimal is because it's an average of all the isotopes. Now, sometimes it depends on your periodic table. They'll have other information there. For example, they may have electronic configuration of the valence electrons. Sometimes there's that and just other things. But this is kind of the minimum information. And then also, sometimes the name is not given. Depends on the class. Okay. Now, the word isotope means the protons are the same. So we can have carbon 12, carbon 14, carbon 11. Those are isotopes. And because they're isotopes, that means automatically protons are the same. Protons identify the elements. When the proton number changes, like in nuclear chemistry, or an atomic bomb, or hydrogen bomb, the element changes. So only carbon can have 6 protons, period, no exceptions. If we add a proton, it becomes nitrogen. We add 2 protons, it becomes oxygen. But you can add or subtract neutrons all day, as long as the protons don't change. And this is real important information. No exceptions. Protons determine the uniqueness of the element. Okay, so let's look at okay, that's 3 isotopes of carbon. Carbon 12 or carbon 14, carbon 10. They all have the same amount of protons. Notice at the bottom, there's 6 on. If it's not 6, it's not carbon. Maybe you can have combinations of neutrons in the nucleus. Now, in the nucleus, It's a very complicated place for all elements, for all atoms. In our class, there are only two things in there, protons and neutrons. Electrons occupy the space outside the nucleus. Okay. But there's bosons and muons, and it goes on and on and on. There are like 28 different ones there. Very complicated. For our class, atom is very simple. Protons, neutrons, electrons. Electrons are outside the nucleus. Protons, neutrons are inside the nucleus. Okay. So the bigger number is a sum of the neutrons and protons. Bottom number, how many protons? So for carbon 12, how many neutrons are in carbon 12? Why 6? Yeah, 6 plus 6, it's 12. Excuse me. Okay, what's the difference between carbon 12 and carbon 14? Neutrons. Which one has more? Carbon 14. How many more does it have than carbon 12? 2. Okay. So the name of carbon 12 is carbon 12. Carbon 12 is the most prolific isotope. And the reason why you can tell that is the molar mass is 12.01. So the molar mass is very close to the most commonly found isotope. So how many particles, let me talk about one more thing first here. It might, yeah, right. Let me check this to make sure. Yes, I am. Okay, so protons have a charge of +1. Electrons have a charge of -1. They're equal in strength, but opposite. Electrons are 1/10,000th the size of a proton. Protons are big compared to electrons. Okay, if the number of protons, positive protons, equals the number of negative electrons, what's the net charge on that atom? 0 or neutral. No, there's no net charge. If they aren't equal, you're going to have a charge. And those are called ions. When the protons do not equal electrons. If you have more protons than electrons, the net charge is going to be positive, and that's called a cation. If you have more negative electrons than protons, it's called an anion. So an easy way to remember that is think of the T in cation, looks like a plus. So you can have isotope ions, neutral isotopes. Neutral has no net charge, 0. Now, if I don't tell you it's neutral, assume it's neutral. Okay, neutral is the kind of common. If it's an ion, I have to tell you two things. I have to tell you whether it's negative or positive, and I have to tell you the charge. So anytime you see it written down or anything like that, there's no common ion. They're all over the place. The +1, +2, +3, etc. They're all over the place. And then I also have to tell you how big a charge is it. Now, let's go back to the periodic table here. Okay. Most of the periodic table is unstable, except for the noble gases. It's made up of three broad, ones that are unstable, three broad areas. Those are metals to the left of the black squiggly line. What do you think the ones to the right of the black squiggly lines are called? Huh? Non-metals. And elements along the black squiggly line are called metalloids. And metalloids take on the characteristics of metals and non-metals, depending on the charge placed on the metalloid. Now, metalloids are horrendously important in our world right now. In 1947, Bell Labs in Illinois, at the University of Illinois, invented something, 1947. Anyone want to take a crack at it, what they invented? No, that's a good guess, though. Something else. Yes, they invented the transistor. That's right. They invented the transistor. Think about where our world would be now if we didn't have electronics. You know, this kind of stuff, have a nice day. Phones, have a nice day. Satellites, all that stuff. And what they replaced vacuum tubes with are transistors. Now, early computers back in about 1944, 45 were two rooms this size. They were huge. They had like 15,000 vacuum tubes. They had to have a room to supply the power to all the vacuum tubes. And they also had to have a room to air condition the room with all the vacuum tubes, because vacuum tubes get very hot. Semiconductors or transistors don't get hot at all. So they waste no energy on heat. Early computers, they were invented to study how ships, cannons land, so they can properly aim them. Also, they used a form of computer to break secret codes. You ever seen the movie Enigma? Anyone seen that? Yeah. Yeah, it's pretty good, wasn't it? Sad, the ending, though. Very interesting, though. And all because of the metalloids. I have a hat that says metalloids are cool. Okay, so what we're going to do now is practice this. We're going to fill this table in. And what I've done in this table is give you the minimum amount of information. And then you need to supply the rest, okay? So let's do one together. Okay, so there's boron there. And boron is located, bless you, right over there, next to carbon. Okay, so looking at boron, how many protons does boron have? 5. What's the atomic number for boron? 5. So those two are always the same, no exceptions. All right, and have I mentioned whether this table has any ions in it? No, so you're going to assume it's neutral then, okay? All right, and what is the name of this particular isotope? Well, it's boron, and it's boron 11. Hmm? Okay, this question was, am I rounding off? No, not rounding off. The isotope has to be an integer. Integer, whole number, no decimals, because you have multiple different ones, different isotopes. And then you average them together, that's how they get the decimal number. That makes sense? You have 5 oranges. You weigh them, divide by 5, right? And if they're not all the same mass, you're going to get a decimal. That's why the isomers are decimal numbers. Same idea, it's because it's an average. Okay, how many electrons does boron 11 have? 5, because remember it's neutral. That means electrons and protons are the same. And what's the atomic mass of boron 11? 11. Okay, the atomic mass is P plus N. Hmm? Neutrons. 5 electrons, 5 protons. Neutrons have no charge. That's why they're called neutrons, neutral charge. Okay. Protons, +1, neutrons, 0, electrons, -1. All right. Now on your test 2, you're going to be doing this on the test. Okay. Again, I'm going to have a subset of this worksheet. Now this worksheet is located files, unit 2. These are all of the worksheets associated with unit 2. And this is the one here that I'm working on. There's also an ionic version as well. Okay, so let's do another one. Let's do the next one down. Okay, atomic number is 11. What element is that? Bless you. If you take out your periodic table from your lab packet, that has names on it. Okay. 11 is on the far left. Sodium. And which isotope of sodium is it? Well, the atomic mass is 24. So that's going to be sodium 24. And how many protons does sodium have? 11. Because atomic number and protons are always equal, no exceptions. And how many neutrons does it have? How many neutrons? 11 plus what is 24? 13. Yeah. 13 and 11 is 24. And how many electrons? 11, because it's neutral. Two reasons. One, it says neutral at the top. And I didn't tell you it was an ion. I didn't tell you it's an ion, it's neutral. I'll try to always tell you it's neutral, but if by some reason I don't tell you it's neutral, then, okay? All right. So let's do one more. A couple other things here. Notice, oh, I have to do the symbol here. So the isotope is protons plus neutrons. Bottom number again is atomic number, or how many protons are there. All right, so why don't you guys, let's spend about 5 minutes doing some of these at your seats. Doesn't matter which ones. Do 2 more. And I'm going to show you when we get into the ions. Ions are, this table is going to be different if they're ions. Who doesn't have a periodic table? Who doesn't have their lab packet? Hmm? Did you need one? I don't have a lot, but I have some. Did you raise your hand? I have one left. Did you need one? Chloe, are you feeling better? Huh? Yes, it is. You're welcome. They're easy to find on the internet as well. Okay, how's everyone doing? Here are the answers. Check your answers real quick. Okay, so let's go on to ions now. Now remember, an ion, electrons and protons are not equal. It's either more protons or more electrons. Okay, so that means the symbol is going to have a charge associated with it. Notice here, on this boron, it's +3. Lead down there is +2. Yttrium is +1. So let's see how they get those. Now, what is the same are protons and neutrons. That's exactly like a neutral. What's different now are the electrons are going to change relative to the proton. Yeah. Where do they come from? That's to do with the charge. Or to get the charge, you need to know the electrons. You need to know one or the other. Is that your question? Yeah, okay. All right. So right now we have 6 neutrons. How many protons? 5. So that's exactly like the other page. Okay, but we have 6 neutrons, so that means atomic mass is 11. So the name is going to be boron 11, just like before. Big difference though, 2 areas. One is there's going to be a charge there if it's an ion. And that's going to determine how many electrons are present. Now, boron says +3. What that means is that there are 3 less electrons. It's kind of the opposite. Electrons come and go, protons do not. Protons determine what that element is. Okay, so if I have 5 protons, how many electrons are in there to give me extra 3? 2. Again, electrons are negative. It's always compared to the protons, though. Protons don't change. So notice the charge. It's a +3. That means we're in the hole 3 electrons. So if it's positive, that means you're lacking electrons. If it's negative, you gained electrons. So that's how to fill up the ion one. Let's do another one. Let's do this one here. Okay. These are always the same. Atomic number and protons all the way down. They're the same. Okay, neutrons. How many neutrons are there? 39 plus what is 89? 50. And what element does that correspond to? Well, let's look up here. 39. That is the one that's hard to spell. Huh? How'd I get it? I would say it ytterbium. So the symbol is going to be Y. 39, 89. And what charge is it? -1. Now you can write -1 two ways. Like that, or just a minus sign. +1 would be +1 or just a positive sign. Hmm? I still don't hear you. '39, '38. Which is more, protons or electrons? Protons. And what charge are protons? +1. It's whatever you have the most of. Yeah. I'm sorry, say again. Yeah, YTTERBIUM. Oh, I see what you mean. You mean the symbol. Is that what you mean? They aren't the same. One's 89, one's 39.
It's this one, but you wrote this one.
Oh, yeah, all right. Yes, I see your point. They're very close. Okay, sorry about that. Okay, so the remaining time, why don't you go ahead and work on this table here? Now, if you have a tablet or something, you can pull up the worksheet. If you go to Canvas Files, Unit 2, towards the bottom, these are there, located there. Want to use your directly, or you can use it up here. Does this make sense?
Yeah, how do I solve for, the ytterbium? How do I solve for, electron? Yeah, how do I solve for electron? I got the neutron.
Electrons were given to you.
Oh, they are 69. Whoops. Well, how do I solve for electrons in general?
I either need to give them to you, or I need to give you the charge.
Right. Right. I see. I get it. Yeah, yeah, yeah.
So on this one, I would have put down +1.
Yeah.
Or I would have put down 38. Excuse me. Yeah, 38 electrons. One or the other.
But you said they're all neutral, like all the problems are neutral.
No, unless I tell you otherwise. And I told everyone that the ions are not neutral because protons don't equal neutrons, excuse me, electrons.
Yeah.
For neutral, it has to be protons, electrons, same. So they cancel each other out. If there's more of one than the other, then you have a charged ion,
So you said for neutral, protons and neutrons have to be.
not protons and neutrons, protons and electrons.
Right. That makes sense.
The charged particles have to be the same.
And then that makes neutrons.
Well, the neutrons are whatever, based on whatever the isotope is.
Like for boron, it's, how did you get it?
Well, that was given.
Right. So like, how do I get? What was it? How do you get 50 neutrons for it? That's you solve it. It's the only way to solve.
Well, because I told you the atomic mass is 89.
Yeah.
And that's equal to protons plus neutrons.
Right. I forgot. Yeah.
So you got 39 and 1, 89, a combination, that means it's 50 neutrons.
Right. Yeah. Thank you.
So this is what we're doing today, everyone. I wanted to cover up to this point.
Is this going to be due as a lab or anything? Is this
No.
going to be great?
Does this make sense? Good.
It's down to, would I write -1, like -1?
How many protons?
Protons
20.
29. And then 27, so there's less electrons than protons. So that would be positive, right?
Exactly.
Sorry, yeah.
By how many?
By 2.
+2 then,
So I
yeah.
would write positive.
Mhm, yeah,
And then for
exactly.
this one, did you put +1 next to this? Why?
Because,
Okay.
see,
Oh, yeah, thanks. Okay, sorry. I just answered. Thank you so much.
Sure.
Can I talk to you after class if you don't mind?
Want to do it now? I didn't mean in here, out there. After class is fine.
Sorry.
I have to put everything away, so it takes a while, so, yeah, just hang around. Just making sense? Good, 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 good. Okay, so look at protons, electrons. Okay, what number is that?
60.
Hmm?
64. Because there's not people in
This is P plus N. So protons plus neutrons is equal to this number here. So these two numbers are always the same. So it's going to be 29. Okay, so look at these two numbers here. Which is bigger? By how many? 2. So it's going to be plus 2. Huh? Exactly, yeah. So if the electrons were 31, it'd be -2 like that there.
You want rounding, so just like for example, like potassium, that would be 39.
No, remember, that's the average of all the isotopes. And an isotope can't have a fractional number of neutrons. It's going to be, so the atomic mass is for a specific isotope is always an integer. When you average them, that's when you get the decimal. You
Do
can
you
keep,
have a hole punch? For this, right?
Hmm?
Do you have a hole punch?
no,
That's a good idea.
periodic table is always handy to have. Huh. How did I get what? Atomic mass for that up there is you add the protons and neutrons. No rounding. Because you can't have part of a neutron.
Photons, give us that.
Yes. And that atomic mass is what the isotope is.
Yeah, I have.
Okay, good. This makes sense. I want an authentic pronunciation of Mendeleev. Right, yeah. Mendeleev.
You don't have this sounds in English because.
Oh, right.
Yeah,
Yeah, it's a guttural thing. Yeah.
it's here.
If you-
Monday and Wednesday people.
Yeah.
Okay.
That's a pretty good lab. Your Monday, Wednesday.
Are we good to go?
Oh, what?
No, I said hi.
Oh. Thought you said I have a question.
Oh, no. It's making sense, but it made sense when you first went over it, and then you started getting into the negatives and positives, and
Right.
it lost.
Yeah, and it's neutral. Protons, electrons, always the same, no exceptions. However, if they're not the same, that's when you create an ion.
How do you know it's the same?
I have to tell you. I have to tell you one of two things. What the charge is, if they're not equal, or the number of electrons.
So how do you find,
The charge,
yes,
okay, which is more, protons or electrons? No, not all the time. Sometimes,
no,
they're more, sometimes electrons are more. If the electrons are more, the charge is going to be negative. If the protons are more, charge is going to be positive. And then the difference is going to be the actual number on the charge. So like 27 and what?
So like the first one you have it there for borons.
Let me get over here so I can see what you're pointing at.
This is 2.
Mhm.
Why is it?
Okay. The charge is +3, right? Okay. That means you have 3 extra protons over electrons. And you have 5 total. That means 2, yeah.
This is your electrons. 39 is one more.
So that would, what would be the charge on that?
Just to check your work, make sure you're doing it. Just add the electrons with the extra amount of charge to get your protons. This is easy. I don't even know why. Do you have a worksheet on this?
2 of them. I have one on neutral, the one I'm showing you up there. Go to Canvas Files, Unit 2, down towards the bottom.
Okay. And is that like homework or something that we have to turn in?
No,
Or is it just practice?
practice. And the answers are there too.
Don't do it like that's to work. It's turn it in. Show me that you know how to do it.
I give you the answers. All my worksheets, I give you the answers.
Sweet.
That's why I don't have you turn in, because everyone want to get on. So there's 2 of them,
Yes.
and then one's neutral and one's ionic.
Okay. So then let's just say you see an electron where it says 20, sorry, 40. The charge would be 3, right?
Wait a minute. Which one are you doing?
So always on a 40. Right next to that 100, that's what I'm counts.
Oh, yeah, okay. +3, yes. Yeah.
I don't know if it's negative. It'll tell you.
No, it'll be more electrons than protons.
So if it was electrons was 43 and protons was 40, it'd be -3.
Exactly.
Help me with the whole like metals, like I want to label this periodic table so that I
Okay,
know where everything's at. I forget.
so squiggly line, those are the metalloids.
So this is metal line.
Yeah.
I just want to have everything right. So right here.
Yep.
What like crosses them? So
Yeah.
this is metal.
Whatever one's metalloids, that's metal. Write out the word metal. And then OID. Yeah, metalloid.
All of this,
No, just the ones that border the squiggly line,
like right here, these ones, like aluminum, gallium,
not gallium.
not gallium.
It'd be boron, aluminum, silicon, only the ones that touch the black squiggly line. So I usually go like that.
Oh, then I'm gonna write it right here.
Okay,
Is that confusing?
everything to the left are metals. That's all of the, all metals.
Even like up to here to beryllium, or like to this area,
No, everything except for hydrogen.
except for hydrogen.
Yeah.
Yeah,
Starting at lithium,
lithium.
all these are metals. And then
And then
a metalloid will change its properties with a voltage applied, positive or negative voltage. That's how a diode works.
Dial.
Diode, di meaning 2. That was the first one they invented.
Okay.
1947 is a diode.
Okay.
And a diode will only conduct if it's got a positive charge on it.
Okay.
And nothing will happen, will act like an insulator with a negative charge,
Okay.
hence the diode,
DIO.
DIODE.
Okay.
And they use that to change alternating current to direct current. Okay, so let me have your pencil. So it's gonna be like this. Those are metals.
Metals.
And then these are the non-metals.
And even helium.
Yep.
Okay, and then the hydrogen, what would that make it? What would
Hydrogen is goofy. Some periodic tables have hydrogen here and over here both. Because it acts like a halogen sometimes, and it acts like a positive one sometimes in acids. So it's kind of weird because it only has one electron. And because of that, it has unique properties. So it's kind of, you can include that with metal. A lot of books will put hydrogen as a metal. And some books don't. So it just depends.
So that one, okay. And then for the categories, like you said, halogens. Is that
Halogens are here.
halogens?
Yeah.
Would be
Noble
just
gases,
Noble gases. And then what are these?
halogens.
Halogens?
Yeah, it's HALOGEN.
Mm,
You're only going to do 4, these 2 and those 2. This is called alkali metals. This is called alkali earth metals. Yeah. So I'm going to give you a periodic table and test, and you're going to have to identify this.
Okay. And then the 1A, the labeling, the whole thing, I forget what it was called. When it goes 1A, 2A, and then 3A, 4A.
Yeah, we're going to talk about that in unit 3, what that
Oh.
means. It has to do with the valence electrons,
Valence.
the group number.
What's valence electrons?
It's the outermost electrons.
Oh.
And there's 2 kinds of electrons, core electrons and valence. Core electrons are extremely stable, so nothing happens with core electron. Valence electrons are not stable. There's certain configurations that are more stable than others, but in general, they're not stable. So that's where all the chemistry takes place, is with valence electrons.
I see.
So nothing happens with cores, and everyone ignores the core.
Okay.
And they're the innermost ones.
Uh-huh.
And I'm going to talk about why one is more stable than the other, why one configuration more stable than the other.
Oh, when is the next test?
Next week, we have a holiday, July 4th.
Okay. July 4th is that Thursday.
So that's when right now the labs are skewed because of the Wednesday holiday. After we go through the July 4th holiday, they'll go back up to normal.
Also, when do we know our test group?
Either this evening or tomorrow morning.
All right.
And if you send me an email, I'll grade yours first.
Okay.
If you want to know, I'm just,
Dude. Curious.
So we have a test on the 18th. So next
You
week,
see
is next week going to be a test or is it the week after that?
I tried it with 8-week semester. I usually go every week and a half, have a test.
Okay. So you're gonna be like,
Yeah, so it'll either be Thursday or Monday.
alright,
Most people like units 2 and 3.
Right.
Because it's not mathy.
okay.
Just don't like that. That problem that I started with, did that make sense the way I did it?
Yeah.
Yeah. This is,
Oh,
no, this is given and you just gotta. This is really an old periodic table. It didn't up. Right, right. Go to internet and find out what that is. Boy, that thing is really old. You see that it goes all the way to here right now. All these are all filled in. Okay, let's break for lab. Thursday lab. Yeah. For today's lab. Today's lab is on the percent composition.
Yeah, I didn't do it. I didn't know what, right.
You didn't know how to do the pre-lab?
I did the pre-lab,
Oh.
I didn't do the first aid section.
Oh, yeah, we're just using table salt.
Okay.
Yeah, I see what you
I
mean
was
now.
scared. Boiling water. You have to write it.
Right. Yeah. These are the two that determine chart. Whichever more, this one's more, it's positive, and then you subtract it to find out by how much. Mhm.
Find the charge.
And the charge is either negative or positive, depending on which you have more of. For what now? Now, if they're equal, then there's charge is 0. There's no charge. Yeah. You have a question? These two are always equal. Doesn't matter if it's neutral or ionic. And then this is P plus N. Oh, you have it right there.
There it's under atomic mass, it's 24 sodium. But it's-
Right.
What is that word?
Remember, this is the average. That's why it's a decimal number. So don't go by the decimal number for atomic mass. Add up protons and neutrons,
To find the
atomic mass, and that's the isotope, the specific isotope. So that means it's going to be sodium. What is it? Sodium. Pull it over here. 24.
Yes. If we're only given the atomic mass and we're trying to find out where.
If you're, well, I added the minimum amount of information. So it depends what else is given.
Oh, protons and neutrons and then give us the atomic mass.
Exactly.
This is find what is closest. Or
No. The decimal number has to do with, it's an average. That's why there's a decimal there. Like if you have 5 oranges, find the average weight of 5 oranges, you add them up, divide by 5. And do you think the oranges are going to be exactly the same weight? It'll be off a little bit. That's why you end up with a decimal number. Same with isotopes. You have all these isotopes. And if you have more of one, then it's going to kind of skew it to that way.
Okay.
Like you had 4 oranges and 1 grape. A grape's really tiny compared to orange, right? So when you look at average, it's going to be really far from the grape. Same with the isotopes. The bigger the isotope number, the more neutrons, or they're bigger.
That makes sense.
Always. Doesn't matter if it's neutral or ion.
Conflict like that.
And that'll tell you the charge, and that charge indicates how many of one or the other you have more of. If it's positive, it means you have more protons. If it's negative, you have more electrons. Because protons are positively charged, electrons are negatively charged. So if the charge is negative, like -2, that means you have 2 extra electrons. Exactly. Good. You're welcome. You're saying you haven't turned it in? Have you scanned them yet? Okay, well, just send me an email and I'll look up whether you turn them in or not.
That was Monday.
Yeah. That way, go home and rest and get better. Yeah. All wet labs require conclusion. All.
Like, turn it in third.
Yes. Conclusion is part of every lab, every wet lab. So scan it, including.
Okay.
And if you've already turned it in without a conclusion, just do it again and it'll replace the one that's there. So you're fine. If you've already scanned it without the conclusion, that's fine. Do the conclusion, rescan it, and then upload it again. And there won't be any deduction. Because I haven't graded it yet anyway, so. The entire lab, yeah.
About conclusion. Not sure I wrote conclusion, but I don't know if it is correct or. Maybe only this one. This session, right?
This is very good, except it's too long.
Long?
You can keep it long like this, that's fine. But on the next lab, do a little shorter one.
But what should I write? Like that part or like this part?
Most people do this part.
This, yeah?
Yeah.
What I did, what I understood.
Yes.
It should be according to purpose, yes?
Exactly,
Oh,
exactly.
okay.
That's very nicely done.
We missed yesterday.
You're gonna do it Monday. So your Monday, Wednesday lab, correct? Yeah. So Thursday's lab is today, it's on percent composition, and you'll do it on Monday. And then the week afterwards, we have July 4th off, and that'll flip it. Because July 4th is on Thursday. So then that gets everyone doing this. The labs are all caught up then. Yeah. No, just sum up what you did. Yeah. And you, I don't want a page and a half, just a pretty good paragraph. That's all. At least 3 sentences, but yeah. Yeah, 3, 4, that's fine.